Anna, please unmute and lead us in prayer so that we can start.
Good evening, everyone.
Good evening. It is
Humble
Anna.
yourselves for our prayer. Kind and loving Father, King of Kings, we thank you for the gift of life. We thank you that you've enabled us come to this day, Heavenly Father. Father, as we are going in for this lesson, may you please bless us with the wisdom and power to understand everything we are going to learn, and may it be useful in wherever we are going to be studying in the lifetime, Heavenly Father. May you please give our teacher energy so that he can give us what is really right and just for us, Heavenly Father, as you gave your people wisdom, Heavenly Father, and you say in Matthew 7:7, seek and ask, and you will be given. Father, we're asking for your knowledge and understanding in this lesson. In Jesus' name we prayed. Amen.
Amen. Thank you, Anna. Good afternoon, everybody. I welcome you to this particular discussion where we are going to continue with our work on complex numbers. Last time when we met, we introduced the complex numbers, went on and tried out a number of things. We added complex numbers. We defined the complex number. We added the complex numbers. We multiplied by scalars. We had several operations on the complex numbers. We found the product and also found the quotients. And we didn't stop there. We even went on and solved a number of equations that led to complex roots. Of course, we learned a number of things. And most important, we went to try an exercise that I left behind. What I would wish to have right now is a feedback on the exercise that you tried. I would want to see those who tried by show of hands. If you tried any numbers, and most importantly, I would want to know if everything went on well, or if there's any challenge that you came across that may require this class to try out together so that we solve the issue that you may have encountered. So can I have a little bit of feedback there? Did you try the exercise? Did you get any issues? Did you find any issues? Was it okay? etc. So please, I want to get the feedback. You can put up your hand and unmute and tell us. Mercy, do you have something to say?
كمان كده ثاني عن أتوال ويا يا
That is why I sometimes end up with a feeling that you should be muted. But anyway, I know you can behave yourselves. So can I have feedback, please? Did you try out the exercise that we left? That's what I want to hear. If you never, please, I'm not going to cane you. I can't. May I still get to know that you never? Yes, anyone there? Can I have the feedback? Is my voice too low? Someone is telling me the voice is too low. Is that right? Am I better now? Can you hear me? Can you hear me, please? Please unmute and talk to me. Jackson,
Yes,
when you...
teacher, we hear you.
Okay. Can I get the feedback? Did you try out the questions that we left behind? That is my issue. Okay, some Adi is saying so far so good, no issues. Thank you, Adi. Anyone else who tried? Anyone else who tried? Okay, Esther, who joined you today, you will have to pick a few things from what we did last time on complex numbers. We are just continuing with complex numbers. Okay, let me just take on a few questions from the same exercise. Especially where I saw where I have interest. Look at which numbers now. If you look at our work and number what, I can share this exercise. Now let me pick for you. I don't have to share. Sorry about that. Find the square roots of the following complex numbers. We saw finding square roots as something that was interesting. Find square roots of the following complex numbers. Someone is left their mic again. Okay, look at this number here. Find the square roots of the following complex numbers. We are saying, let us do the first part. Here we are finding square roots of 5 plus root. The square root of 5 plus 12i. Now, last time, what did we say? We said that the square root of 5 plus 12i is, if you let, so this is our solution. Let x plus iy be the square root of 5 plus 12i. So if the square root of 5 plus 12i is x plus iy, our duty is to find the value of x and also find the value of y. How do we solve this? Square both sides. And when we square both sides, what do we find? When we square both sides, we shall find that when I square x plus iy, it should give me the square of this square root. And when I square the square root, I get that value 5 plus that. So what more did we say we do? Then we go ahead, and when we go ahead, we square. We shall get x squared when we square. Then we shall get x. When you square, what do you get? You get x squared. Then you get twice I xy. Then you get I squared y squared. And this is equal to 5 plus 12i. Now, when you take the I squared, which is actually -1, our I squared here, this I squared that you see here is actually -1. So when you put -1, what are you going to get? You are going to get that x squared minus y squared plus 2i xy. This is 5 plus 12i. Two complex numbers are equal only if their real parts are equal. So that implies to us that the x squared minus y squared is actually equal to 5. This I can name to be my first equation. And also if their imaginary parts are equal, meaning that 2xy is actually equal to 12. From which xy is what? Xy is 6. This is my second equation. The reason why I'm naming my equations 1 and 2 is because I want you to take a note of the fact that I can only solve those two equations now. I use simultaneous methods of solving simultaneous equations. So from the second equation, from equation 2, from equation 2, what do I have? I have that x will be equal to 6 over y. I substitute that in the first equation, and I square, I get 36 over y squared minus y squared. We can mute ourselves, please, so that we go on with the lesson without those challenges. Please mute yourself. We have people who have very poor networks that keep producing a lot of noise. Please mute. Okay. Then we can go on and solve that equation. If I multiply through by y squared, then I'll get a quadratic equation, quadratic in y squared. Someone else last time told me, let y squared equal to some other variable. There's nothing wrong with that. You can go ahead and let it equal to some other variable. But when I multiply through by y squared, to 36 minus y to power 4, which is actually equal to 5y squared. This kind of equation is quadratic in y squared, and so you can only, what is important is for you to reorganize. If I carry y to power 4 to the other side, it will produce y to power 4. The 5 is already there, positive 5y squared. And the 36, when I carry it to the other side, it becomes negative And that gives me 0. The factors of negative 36, which give me positive 5, are positive 9. So y squared is plus 9, and also negative 4. So y squared minus 4, and this is equal to 0. Those are the factors of 36, positive 9 and negative 4, giving me negative 36. Factors of negative 36, but adding up to 5. So what does that then mean? It means that either the y squared is negative 9, or the y squared is 4. Now, the y squared is negative 9 is going to give us a value that is not real. Please reject that, because in the complex number x plus iy, the x and y must be real. So that's why we are taking y squared is 4. Therefore, y squared is 4, rejecting negative 9, from which our y is equal to the square root of 4, which is plus or minus 2. Now that I have y, I can go back from the first equation, the second equation, I think. From there, where we got x is equal to 6 over y, and I get the values of x. So when y is 2, it goes without mention that x is 6 over 2 and is 3. And when y is negative 2, in the same spirit, x is 6 out of negative 2, and it produces a negative 3. So what are our square roots? Our final square roots for 5 plus 12i are x, which is 3, plus 2i, all negative 3. So it's a plus or minus this. So all negative 3 minus 2i. Those are the square roots. Plus or minus the 2 square roots of 5 plus 12i are plus or minus 3 plus 2i. Unless there's a question, I can beg you to move on. Someone requested that we try a question from one question from number 10. I don't know why. You can try and see. Someone is saying, Grace, why do I get opposite values? Grace, what do you mean by opposite values? Because your x should be 3, your y should be, I think that is what it should be, even when you make x the subject, Grace. Please check yourself, Grace, check yourself and see. Is everyone comfortable there? Should I try the number 10? Can you unmute and talk to me? Yes, Grace.
Good afternoon, sir.
Good afternoon, Grace.
So I let x be the subject, and my value of x squared.
You let x be the subject, but that's what I've done also. I let x be the subject. What do you mean? In which equation?
No, after getting equation 2, I let y.
Okay. So you said Y will be equal to what?
6 out of x.
Yes, and what did you write thereafter?
So it was x squared minus 6 out of x into
6 out of x, but it is also squared.
equals to 5.
But are you not saying 6 out of x is squared?
Yeah, it is squared.
So what did you get thereafter?
Yeah, when I got the equation, which was x power 4 minus 5x squared minus 36.
X power 4 minus 5x squared
Minus 36.
minus 36 is 0.
Mm.
That is okay. I'm
Is it
moving
okay?
on. Yes.
Because your equation was y power 4 plus 5, yet mine is minus 5x squared.
But for you are looking for x, me,
Oh.
I was looking for y. And
Mm.
so that is why we have those differences.
Okay, sir.
There's nothing wrong with that. So you are getting
Thank
x, I was getting y.
you.
Is that all right?
Yeah, it's all right.
So you should move on. There's nothing wrong with that.
Mm.
Okay. Hope that is taking us. We are moving better. With Grace having a few issues there, which we are now saying they are normal. Those Grace issues are normal. Okay. Someone is saying in number 10, but before. So how do you get the values of y squared? Joy Esther, what is it that you are exactly asking? Esther, after missing last week, what are you asking? Can you talk about it? Because you're saying, how do you get the values of y squared? You solve the quadratic equation, and then you get the values of y squared, and then you get the square root to get the value of y. Then you move on. I think you can, Joy Esther. Okay, and an example from number 10, someone is saying, can you try out numbers from number 10? I don't know what they have. Solve the following equations. All have at least one real root. Number 10 is having a cubic equation, and you can solve. The cubic equation, you can solve. Solve the following. I hope someone is saying from here. I can pick this. I don't know whether you all have them. And those are the equations. Okay. Solve the following equations. All have at least one real root. What is important for us is to take note of the fact. I want us to solve part A together. I want us to solve part A together. Part A. This is the part A. So if we had solved part A, that is what we shall be solving. Solve this equation here. What do we have for part A? For part A, I don't know whether it is clear for everybody. It's not so clear for me. I wonder how I should make it clearer. Part A is having that bit there. that we are solving the cubic equation. Our equation, I don't like copying the question again. I have nothing to do because I don't feel very comfortable. Is x cubed minus 7x squared plus 19x minus 13 is equal to 0. Now, this is a cubic equation. How do you handle cubic equations? If I may toss it back to you. How do you handle cubic equations? Someone to give us how they handle cubic equations? Did you hear my question? How do you handle cubic equations? That's the question. Riyadh is saying factorize the constant. The constant is 13 and it has two factors, 1 and 13. So Riyadh, where do I go there after? Katz is saying press a calculator. Okay, that is another way. Press a calculator. And what do others say? Riyadh is saying substitute the factors into x and look for one which gives 0. Okay. We can use long division method. We first get the values. Okay. Now, if I substitute trial and error, x is 1, what do I get on the left-hand side? My left-hand side will give me 1 to power 3 minus 7 times 1 squared plus 19 times 1 minus 13. When you simplify this, you'll get 1 minus 7 plus 19 minus 13, which actually gives us 0. Which is 0 is what we have on the right-hand side of this equation. So it means that the value x equals to 1 satisfies the equation. And if the value x equals to 1 satisfies the equation, then it goes without mention that our x is 1 satisfies, our x equals to 1 satisfies, meaning or implying that our x minus 1 it will be 0, and so x minus 1 is a factor. X minus 1 is a factor of our equation. So if x minus 1 is a factor for that expression, then other factors can be obtained from long division. Someone said long division. Other factors will be obtained from long division. Okay. And when we move on, what do we find? When we move on, what we find is that when I use long division, I'll get x cubed minus 7x squared plus 19 minus 13 and divide it by x minus 1. So we are finding that the factor is x minus 1. And we are having x cubed minus 7x minus 7x squared, and then plus 19x plus 19x, then plus minus 13. Okay. Long division, what does it give to us? Long division, what does it give to us? Okay. Long division will give us x cubed divided by x minus 1. So we divide this by that. We shall get x cubed divided by x, which gives us x squared. Then we take that x squared and we will multiply through by the whole x minus 1. And it will give us x cubed minus x squared. Then we subtract. That's our long division. X cubed minus x cubed will go. And then we shall have negative 7x squared minus negative x squared. This will give us negative 6x squared. Yes, Juliet?
So I have not understood how to get that factor.
Juliet, when I look at the chart, I can see people who are saying, how do I get those values of x which satisfy the equation? With the cubic functions, the first value of x that satisfies the equation is obtained by trial and error method. But whereas it is trial and error, we usually call it intelligent guesswork. So we call it inspection. You don't just guess anyhow. So it is inspection. You look at values that can bring you that can give you the zero. But in most cases, those values must be factors of that 13, which was our constant term. So like we do for the quadratic, you get the 13 multiplied by the coefficient of x cubed, and you get factors. In most cases, it would be one of those factors will satisfy. So in this particular case, I picked on a 1, substituted the 1, and the 1 gave me 0. When it gives me 0, it means that the x is equal to 1 is a root. This is a root of the equation. But then when I bring the minus 1 to this side and get 0, when I bring the 1 over to this side, I will get x minus 1 equals to 0. But the issue I'm interested in is that the x minus 1 is one of the factors of the cubic equation that I'm factorizing, whose roots I'm getting. Because when we have those factors, that's when we can comfortably say that when you multiply those factors, you are getting 0. So one of the factors is 0, or all of the factors are 0, something like that. So I get x minus 1 to be a factor. And then I use that x minus 1 and divide by the expression. And that is when long division comes in. And while I'm long dividing, I am doing exactly what you have been, from the beginning, from your, I'll divide this x cube that you see here by this x. Come up with the x squared that you see there. Take the x squared, multiply by the dividend, the divisor x minus 1. And that's when I came up with this x cubed minus x squared. Now I am subtracting. X cubed minus x cubed is 0. Negative 7x squared minus x squared minus negative x squared, which gives us negative 6x squared. Then I add the 19, drop 19, you can even drop the 13, and divide. So next we are going to keep dropping and dividing. Dropping and dividing. So when you drop and you divide, what do you get? When you drop and divide, you are going to take the negative 6 squared, this negative 6 squared, and you divide it by, you take the negative 6x squared, and you'll go back and divide it by this x here to give you negative 6x. Then you multiply out. It will give you negative 6x squared when you multiply negative 6x by x. And when you multiply negative 6x by negative 1, it will give you positive 6x. Again, subtract. The negative 6x squared will leave, will disappear, and we shall remain with 19x minus 6x. 19x minus 6x will give us 13x, and we shall drop the negative 13. And when we divide again, we shall get positive 13 here, and we shall multiply out to get 13x minus 13. And our celebrations can begin when we see that actually the result out of that subtraction, final subtraction, is 0. Because what makes a factor is the factor having the remainder 0. So you can see the remainder 0 then coming out. So what are our factors? So it means that our x cubed minus 7x squared plus 19x minus 13 is 0. As factors, x minus 1 and also x squared minus 6x minus 13, giving you 0. So either x minus 1 is 0, from which x is 1, or x squared minus 6x plus 3. X squared minus 6x minus 13 is 0. Now, when you look for factors of 13 that give you negative 6, they are not existent. And if they are not existent, then you are going to solve that quadratic equation using a general method, x equals to negative b plus or minus the square root of b squared minus 4ac all over 2a, which will give us negative b. The b is already negative 6, so negative b becomes positive 6, plus or minus the square root of b squared, so positive 6 squared, minus 4 into a, which is 1, into c, which is negative 13. The root of all this, all is over 2a. And our a is another 1. So we're going to come up with this thing here giving you 6 plus or minus the square root of 6 minus 52. That is 6 minus 52 all over 2. This will give you 6 plus or minus the square root of negative 1. What is 36 minus 52? Negative 16. Thank you very much. Negative 16 all over 2, which finally gives us, before I divide the 6 plus or minus 4i, the square root of negative 16 is 4i all over 2. And we shall have, when we divide it, is 3 plus 2i all 3 minus 2i. So the three roots of this equation, because it is a cubic equation, the values of x are, the first one was the real root 1, and these 2, where 1 is actually a conjugate of the other, because we were told complex roots appear in conjugate pairs. Yes, Emma?
Is 13 a positive or a negative?
Emma, what do you see? Emma, what do you see? From which level are you?
Of the division, the 13 was a positive.
At this level here, eh? Yes, 13 is positive. So go with the positive 13 to this level. Then move on with the positive 13 to this level. And unfortunately, I made another error which corrected it, because it is positive 13 that can give us negative 52. I made another error. That's why I am safe. Okay, it is the positive, and it will give us negative 52, unfortunately, minus 4ac. Yes, that is negative 52. It gives me negative 16, which gives me 4i. So it is a positive 13, thank you. Yes, there is someone whose hand is up. Please rename. You are above the thing of calling yourself Techno. You can always rename. If you can't, let me rename for you. Give me the name. Okay, tell us what you want to say.
I'm lost on the third step.
In the first case, what is your name?
I'm called Arnold.
Arnold, can you rename? Okay, come again. What is your question?
Okay.
What is your question? Arnold, what is your question? Arnold. Arnold, I will rename it for you. What is your question? Arnold has disappeared. Any other question? Arnold, you can type in the chat. Any other method for solving which ones? Someone is saying any other method for solving cubic equations? Madrid, what is your problem? Cubic equations, you will get the first solution by trial and error, or by inspection, or by intelligent guesswork. And then you will go ahead and solve the rest of, and obtain the rest of the solutions. Okay. That was picking from last week's lesson. May I request that I move on and have some little bit of new work? Yes, Maureen, Madrin, just like we have just done. Okay. Doctor and other people there are saying, yeah, let's go on and pick on some simple piece of work. So what simple piece of work do we pick on? We can move on just a little and do what? We can move on just a little and move on with this piece of work. Okay, what more can we go on with? If you looked at our work, we have some geometrical representations in our book. And what is interesting with the geometrical representations is that you will find geometrical presentation. You will take a note that complex numbers can be represented on a diagram. And when you represent them on a diagram, what do you see? What you see is that you can use the X and Y axes to represent. Just a minute. Please give me just a minute. Just a minute. Sorry, I apologize for that. Some people were disturbing here and I had to clear. But now we can go on. We can represent a complex number on a diagram on X and Y axis. The axes are not X and Y when we choose to do so. The X is called the real axis. The real axis, and the Y is called the imaginary axis. So this is imaginary, and this here is real. Imaginary, real axis. And this is the real axis. The other is the imaginary axis. So you can represent complex numbers on axes. One is real, the other is imaginary, and then you have a complex number. So a complex number, Z, which is A plus IB, will be represented as A here, and B on the imaginary. The real part is A, the imaginary part is B, and this is the point. And from the origin to there, from the origin to there, I'll have my complex number, which is Z, where Z is A plus IB. I can have a sum of complex numbers, two complex numbers, Z1 and Z2, for instance, in exactly the same way. If I have this as my imaginary axis, and this is my real axis, then I'll have my complex number here. This is imaginary. This is real. And if I have two complex numbers, one there, the other one here. So if I have this as Z1, then the sum of those two written will be obtained when you add that to that, and also this here to that. The way we add the vectors. So this here is the sum of those two complex numbers. So you have a complex number here being Z1 plus Z2. So the sum of complex numbers can also be obtained the way we obtained. So this is the Z1 plus Z2 or the Z2 plus Z1 here. When you add those two, the sum becomes the sum will be obtained there. And then okay, I'm sorry. I can see a number of things on the chat. Brian, please go ahead and say what you want to say.
I have a question.
Yes, please.
So when you're adding, what about if I first plot Z1, then I plot Z2 and Z1, so that where I stop is the Z1 plus Z2?
That is okay. My point there is that the Z1 is added, the Z2 is added after, it continues where Z1 stops. All where
Yes.
Z2 stops, the Z1 continues, because we know addition is commutative. Whether I add Z1 to Z2 or Z2 to Z1, I should be getting the same thing. So you can add Z2 to Z1 where Z1 stops, or you can add Z1 to Z2 where Z2 stops. It is very okay, and that is what I am showing exactly. That's the sum of two complex numbers. And
Yes, I
then
get.
I can talk about also the difference, just briefly. The difference is also almost the same, because if I have my imaginary axis here, and my real axis here, this is imaginary, this is real. This is imaginary. This here is the real. And when you have two complex numbers, one here and the other way. I can't have in a meeting. And the second one here, then what are you going to have? We are going to have and B may be there, something like that. So if one is Z1 and the other is Z2, if one is Z1 and the other is Z2, Then the complex number that comes here. Depending now on where you make it face. If I make it face this way, if it faces this side, then it will be from this end of Z1 to the end of Z2. And it will move from Z1 to origin to move like this and come to this side. So it will be positive Z2, negative Z1. But if someone chooses to change its direction of motion, someone chooses to change its direction of motion, then what you are going to have is this is imaginary, this is real. One complex number is there. The other complex number is here. And then you choose. Change this to that side. This is my Z1, sorry. Sorry for that. My Z1 is this one. My Z2 is this one. But then the direction is changed. So it means it starts from this side, moves on to this way, and then later on continues to that side. So the positive Z1, the Z1 is the positive, the Z2 is the negative. So you end up with Z1 minus Z2. So the directions are very important in charging us there with which one is positive and which one is negative. And we can then be there anyway, finally. I can see a lot of the issues of literature class. I wonder why. But anyway, let's continue with the geometrical representations of our complex numbers. You can also see products of complex numbers if I took the complex number in the modulus argument form. I think I should first introduce the modulus argument form. What is a modulus of a complex number? Then we can come up with modulus argument form. So I can talk about the modulus. Of a complex number that if my complex number is z, which is equal to a plus ib, the modulus refers to the magnitude. Modulus is the magnitude of the complex number. It is denoted as this. And from Pythagoras, I have, this is my A on the real, and this is my B on the imaginary, and this is a complex number. So this angle, which the complex number makes, in the first place, this is the right angle, and the modulus can be obtained from that length there for the hypotenuse. and it will be a squared plus b squared square root, the length of that hypotenuse. In the same way, the argument of the complex number of z, which is a plus ib, is the angle a plus ib. The argument is the angle, and it is the angle which the complex which the vector, radius vector for the complex number makes with positive real axis. This is the imaginary axis. This is the positive real axis. The angle that it makes with the positive real axis is the argument of the complex number. And that argument of the complex number, we denote it as arg, because we are looking at the principal value of that angle. Because for us who know trigonometry, we know that there are very many angles which you can get if you are solving that equation that tan theta is equal to obtain theta. Tan theta is opposite of adjacent. So we have that principal angle, which is obtained from tan inverse of b over a. But the argument argz refers to the angle that lies between negative pi and a pi. And like I have already indicated it here, negative pi and pi, it is a measure in radians. This angle is a measure in radians. It should be given in radians. So that is argument and modulus. And I can finally then say that if I have a complex number, this is my imaginary, this is my real, represented on the Gann diagram. Then here, this is A, this is B, and this is theta. If the modulus of this complex number A plus IB is denoted by R, and the argument is denoted by theta, then we can comfortably say that from resolving to obtain the components from cosine theta equals to adjacent out of hypotenuse, my adjacent, which is the A and it is the real part of the complex number, is R cos theta. And in the same way, sine theta equals to opposite out of hypotenuse by B, which is the imaginary part of the complex number, is R sine theta. So I can write my complex number in modulus argument form. So my Z, which is A plus IB, can be written as R cos theta plus IR sine theta, which is R, then cos theta plus I sine theta, and that is what we call the modulus argument form. So where r is the modulus and theta is the argument of the complex number. A complex number can be written in that form there. Okay, let me look through the messages just to see which messages they are here. I think it's the same messages that I have. Okay. That is that is what I wanted us to see. And then we can move on and continue. Someone is asking about the recording. The recording Mr. Stephen will share. Stephen will share the recording, Mr. Kazio. But unfortunately, we have a number of people who are disrespecting us when someone opens the mic and makes noise and closes. You see that is uncouth, and we can't allow that kind of behavior. But anyway, for the sake of us who are behaving, we could then continue and share just a few other things. Okay. If I give you an example here, unfortunately I don't have it in my soft book. Soft book misses that page. I think it wasn't taken. But you can write it. Find the modulus and the principal argument of. Finding it is an example in our book, by the way. Find the modulus. Telling us to find the modulus. And the principal value of the argument. Find the modulus and the principal argument. Of the first part is giving us 1 plus I. Part A is giving us 1 plus I. What is the modulus in the principal value or the principal argument of that? If you were to be keen, you would notice that if you are to sketch that or to represent it on an Gandhi diagram, and I think I didn't mention that when you represent your complex number on as a geometrical figure, we say you have represented it on a Gandhi diagram. On those axes where you put it, we call them, we say it's an Gandhi diagram. So on an Gandhi diagram, this here will have 1 unit. To have 1 unit there. That is the imaginary, this is the real. So to have 1 unit on the real, it will also have 1 unit on the imaginary. And so it comes somewhere there. With 1 unit on both sides. 1 there, 1 there. So that is the 1 plus I. So the magnitude of this here, this is my Z, which is 1 plus I. Its modulus Z will be from Pythagoras. 1 squared plus 1 squared square root. 1 squared plus 1 squared, then square root. That's a modulus. So which will actually end up as 1 plus 1, which is 2 square root. And then beyond that, what more do I have? Beyond that, the argument, principal argument is this angle. And that tan theta is 1 over 1. And theta is the tan inverse 1 over 1, which is actually 45 degrees. But we want it in radians. So this is why we are dividing by 180 times pi. So that we have it in what? In radians. And when you simplify that one, you get pi by 4. So the principal argument is lies in the range negative pi to pi. And if I'm now to represent this complex number 1 plus I in modulus argument form, the modulus is root 2. The argument is the pi by 4 plus I sine pi by 4. And that gives you the modulus argument form of that complex number. So it's just a matter of obtaining the modulus in radians. Your calculators have that measure of an angle in radians. You can just go to the calculator, put in radians, where we have deg, radian, and also deg, then rad, and then grad. But we are now interested in rad, where you can put in that model to get the angle, but that will not give you in terms of pi, but it will give you whatever something point something is. To give you those points. But you can also get it in degrees and convert it to radians in your own. You can get it in degrees and convert it to radians. When I'm using Pythagoras to get the modulus, I don't use the I use the, what do I use? I use the imaginary part and also the real part, but not, the I is simply showing me what the imaginary part is. But I use the imaginary part and also the real part. I am interested in the length there. And then you can go ahead and finish up. Yes, someone is saying on the part of getting the angle, are we considering the real and the imaginary? Yes. The real is the adjacent and the imaginary is the opposite. So you can always use them and you get the angle, and that angle is what we call the argument of the complex number. But make sure you get the angle which the complex number makes with the positive real axis, not any angle. The one that is made, but it should lie between negative 180 and positive 180 in degrees. Convert it to radians so that it is negative pi to positive pi. I think that is what I've seen there. So you can go through those other parts of that as they are given there. Part B was talking about negative, the complex number, negative 3 plus 4i. That was our part B. Write it in modulus argument form, for instance, or get the modulus. So the modulus for this, like someone has said, it will be negative 3, the real part squared, plus the imaginary part squared, square root. So leave The I does not come along. So this is 9 and 16 square root, which is the square root of 25, which is 5. That's the modulus or the magnitude. And after getting the magnitude, get the angle. Now, if I come in to get the angle, you will notice that for this complex number, what do I see? I see 3 minus 4i or negative 3 plus 4i, I don't remember. It's negative 3 plus 4i. So the negative 3 is on this side and the 4 is on this side. So it could be something like maybe something like this. Oh, sorry. Where I have negative 3 here, and where I have 4 there, this is the origin. So I'll have the argument as this angle, which the radius vector, which this complex number makes with the positive real axis. That's the number that you must get. But the modulus is okay, 5, but the argument is that angle. So in other words, you are going to end up getting this one on this side, which is alpha. If I'm to get alpha, my alpha will be the tan inverse of the opposite, which my opposite is 4 over 3. Now after getting that one, then I'll take pi, the 1/8, and subtract the alpha. I'll take pi and take away the alpha, so that I get the angle as my theta, which is the argument. My theta, which is the argument, is going to be pi minus the tan inverse of 4 over 3. All of them are in what? In radians. So that gives you the angle that is the principal argument there, arg z, and then you can represent your complex number negative 3 plus 4i in modulus argument form as r, which is 5, into the cosine of that theta plus I sine that theta, where theta is pi minus that angle there, which is tan inverse 4 over 3 in the radians. So that gives you the theta. So in modulus argument form, that is what we expect you to do. And any other angle, you can get it through that. For instance, yes, there's someone whose hand is up. Please, can you open and talk to us?
So
Riyadh?
I was asking, isn't there 3 negative? Shouldn't it be tan inverse of 4 over negative 3?
When I'm considering this angle, the way I've drawn it, if you are considering this angle, sorry about that. If I'm considering this angle here, somewhere there, and I'm only looking for this angle, then if I take the negative 3, then I will not be getting this angle. Remember, in some of these things, you are interested in this will be 4 and this will be 3. It is true it is negative on this side, but I'm interested only in the value of the angle theta. And if I'm interested only in the value of the angle theta, I'm interested in that length. How long is that distance? So it is the same thing that I want you to get the same angle as if you had obtained it on this side. So if this is 3 and this is 4, This is the same angle you would have got even if it is on this side. The two are equal. But if you make it -3, then you are going to actually look for the other angle, the other side. So I'm avoiding that cramming. I want you to work out something that you are looking at, that you are seeing. That is why I'm using that. And then going ahead to obtain 180 and subtract that angle. I think you can see that the two angles are equal, whether it is on the negative side or on the positive side. So the negative is not important. What is important is the value of the angle. Yes, I can see people asking here. So when I want to get the angle direct in radians, I change the mode of the calculator. Yes. Your final answer will be in radians, though the calculator doesn't give you any chance to use the pi. Someone else is saying, what are you saying? Is that the 3 negative? That's Riyadh. Riyadh, I have answered you. How do you know that you are supposed to consider? What is that? That and that n and not alpha. Can you, that theta and the angle that we want is always the angle between the vector and the positive real axis. That's why I took the angle on the other side, because I'm getting the angle with the positive real axis. I think the angle becomes a negative. Pi minus that angle will remain positive. Negative angles are supposed to be the ones now. From here, if I took the angle to this side, it would be negative. If I was taking it this way, all here. The sense where you are measuring the angle is what makes it plus or minus. If you measure in the clockwise sense, it will be negative. But where you are, that angle is positive. And finally, yeah, someone has it in degrees. I'm getting 126.87. That one is in degrees. Convert it to radians. I hope everyone knows here how to convert from degrees to radians. What else is someone getting? I'm getting, I beg your pardon, an argument of the last number. I think I have mentioned the number of things and I could have answered you. Is it a must to represent the answer in radians? Yes. If it is the argument of a complex number, it is a must that you represent it in radians. Theta and alpha, I have talked about theta and alpha. Talked about the 126.87. And we beg your pardon, I didn't understand it while it required. But I hope it is one of the questions that you later on asked. Maybe I have answered it. Okay. Now, that's done. What more do we have? What other thing do we have? We have an example here, which I have in my book. And I can give you to copy. Now someone is telling me 7/10 pi, no problem. If that is what you get, I don't have whatever now, that is Riyadh. Though I wonder how you get 7/10 sharp exact. Riyadh, I don't exact that 126 point whatever to be exact. The 7/10 is so exact. I would expect something much more with more decimal places there. Okay, Riyadh, yes, say something.
The answer on the calc is 0.7048. pi. So I just took these first three digits to make it 7/10. But it's 0
You are over rounding off. Can you read?
0,
Can you leave it at 0.7?
0,
0,
48
4, 8.
pi.
Fine. Thank you very much. Don't over round it off. Leave it like that. That's far better than 7/10. Thank you, Riyad. Okay. And it's a positive value for our kid for that matter. Let me copy this question, then we go through it. I hope we shall have enough time. We still have enough time. What do we have here? When I look at this question, example 20. What do I have in my example? Prove that for complex numbers, sorry about that, prove that for complex numbers, prove that for complex numbers Z1 and Z2, modulus Z1 times Z2 is equal to that and argument. Now, for that solution, what would I expect? And the solution for that? If Z1 is written in modulus argument form as R1 cos theta 1 plus I sin theta 1 and Z2 is written as R2 cos theta 2 plus I sin theta 2. The product Z1, Z2 will give us R1 cos theta 1 plus I sin theta 2 into R2 cos theta 2 plus I sin theta 2. And this will give you R1, R2. And when you multiply those ones, you get cos theta 1 cos theta 2 if you open the brackets. Cos theta 1 times cos theta 2. Then you have cos theta 1. No, you'll have I sin and I sin, which gives you I squared, which is -1. Then you have sin theta 1, sin theta 2. Then you take cos theta 1 and multiply it by I sin theta 2, and to give you I into, I think I should begin with this one here, sin theta 2, sin theta 1, sorry, this here is theta 1, sorry about that, this here is theta 1, this here is theta 1, so it will be sin theta 1 will be sine theta 1 cos theta 2 plus cos theta 1 sine theta 2. And so just into this, and all of this is in one big bracket. So finally, what do I expect you to get? Oh, let's shift this up here. Sorry about that. So from down here, if you can come up here, what are you going to get? You can see that R1, R2. What did I want to mention here? You can see that the cosine, cos theta 1, cos theta 2, minus sine theta 1, sine theta 2, sine theta 2. From our trigonometry, we give you the cosine of theta 1 plus theta 2 plus I the sine of, and the sine theta 1 also this one, cos theta 2 into this one will give you theta 1 plus theta 2. But all of this is multiplied by R1, R2. So what does it mean? It means that the modulus of Z1, Z2 is R1, R2. R1 is modulus Z1, and R2 is modulus Z2, Z2. So what does that mean? It means that the modulus of the product of the complex numbers is the same as getting the moduli of each and multiplying them. When you get the modulus of Z1 and you get the modulus of Z2, then you multiply the two, it gives you that product, which is the modulus of the product of the complex numbers. Those two things are different. Those two things are different. Please take a note. But they are giving the same result. That when I multiply the complex numbers and then I get their modulus, I'll get it will be the same thing as when I get the product of the moduluses. These days, the English developed to moduluses. But if you are not comfortable, the product of the moduli of the individual complex numbers Z1 and Z2. Then the second one that I wanted you to take a note of, and seriously, is also the argument. If you look at the argument of the complex numbers, the argument of the product of complex numbers Z1 and Z2 is theta 1 plus theta 2. But theta 1 is actually argument Z1, arg Z1 plus arg Z2. So when you multiply two complex numbers, you add their arguments. During multiplication, the arguments of the complex numbers is added. But the moduli says are what? Are multiplied. I don't know whether you're following there. I can see someone who is saying they are lost, Bavidia. Bavidia is my daughter. So let me give you one simple example where you can use this business here. When someone tells you to, if someone gives you Z1, look at this. Z1 is 3. That's the modulus. Cos of pi by 3. That's the argument. Plus I sine pi by 3. That's our Z1 in modulus argument form. Then what about our Z2? Our Z2 is pi, which is our argument, into the cosine of pi by 4, which is our argument, and I sine pi by 4. Pi is our modulus, pi by 4 is our argument. And they tell you, obtain the complex number Z1 times Z2. So in the first place, you're going to obtain the modulus of that product. And the modulus of that product is obtained by taking the modulus of Z1 times the modulus of Z2. The modulus of Z1 is 3. The modulus of Z2 is 5, giving us the modulus of the product as 15. That is very important. In the second place, you are going to say what is the argument of the product of these complex numbers, Z1 times Z2. We are saying get the argument of the first complex number and add it to the argument of the second complex number. And this will give you the argument of the first one is pi by 3. The argument of the second one is pi by 4. And when you add, you get 4 pi plus 3 pi out of 12. And when you add, it gives you 7 out of 12 pi, or 7 pi out of 4. Then, when all that is done, then you can write Z1. Take a note of the fact that 7 pi out of 12 has not exceeded pi. So it is in the range negative pi to pi. So it follows in the range. If it exceeds, then you have to find it to go to a diagram and get the angle that lies in the range. Anyway, finally, what comes up? To get Z1 times Z2, you get its modulus, which is 15, and you will multiply it by the cos of its argument, which is 7 pi over 12, plus I into sine its argument, which is 7 pi out of 12. So that is the product of the two complex numbers. Take note, during multiplication of the two complex numbers, you end up multiplying the moduluses, and you end up adding to obtain the principal argument of the product. And you'll be there when you get the value as fast as that. Now take a note that during the division of two complex numbers, Z1 over Z2, in the same way, the modulus of that quotient will be the modulus of Z1 divided modulus of Z2. That is in the same way. And during the same division quotient, Z1 out of Z2, the argument with the argument Z1 minus arg Z1 minus arg Z. So please go ahead and take note of those small. When we are multiplying, the arguments are added, the moduluses are multiplied. When we are dividing, the moduluses are divided, the arguments are subtracted. Those are very important results. And from these results, what do we get? When I have Z squared, it means its modulus is going to be the modulus of Z times the modulus of Z. So it is going to be the modulus of Z squared. The argument of Z squared will also be argument Z plus argument Z. Which is twice the argument of Z. Now, if the complex number Z has a modulus R, then this is going to be R squared, and also has the argument theta. This is going to be twice the theta. There is a very important statement that we have made there. What is that important statement? That important statement is that important statement is that if Z is the complex number with modulus R and argument theta, and so can be represented in modulus argument form as this, then when you square Z, you will square R, and here you will double the argument, and you will also have the argument doubled here, get you that. Now, may I ask for your contributions from that knowledge? Can you give me Z cubed? Can I have Z cubed from that knowledge? Yes, someone with a hand up.
Into cos 3 theta plus
Your network
I
was not
sin
clear.
3.
Can you come again? Babide?
R cubed into 3 cos 3 theta plus I sin 3 theta into cos 3 theta plus I sin 3 theta.
Very, very good. I feel nice, Babide, for that.
Okay.
Let me get Z to power 4 from someone else. Hand up. Z to power 4, what does it give to us? Yes, Provia.
R power 4
R power 4
into cos 4 theta
cos 4 theta
plus I sin
plus sin 4 theta. Thank you. And now I want someone to give me, I can't know who you are as such. I was going to say I want a boy, but anyway, whoever is ready. What is Z to power N? Yes, Juliet? Juliet, did you put up your hand first?
Yes.
Ozie, okay, Juliet is coming. Finally, yes? R
Power N
power N
into brackets cos n theta
cos N theta.
plus I sin n theta.
Beautiful, Juliet.
Okay.
Now let me say that if you take R to be 1, the modulus of the complex number to be 1, then you are actually going to come up with this statement that says that when I have cosine theta plus I sine theta, and I raise it to power 2, because my R is 1, this gives me cos 2 theta plus I sine 2 theta. Can I have someone tell me what it would be if I took cos theta plus I sine theta and I raised it to power 5? What would I have? Yes, Mary Grace.
It is cos 5 theta
It is cos 5 theta
plus I sin 5 theta.
plus I sine 5 theta. Thank you very much. That is great. As I wind up, what is the value of cos theta plus I sine theta raised to power n? What does it give to us?
Cos n theta.
Dr. Pretty, let me see Dr. Pretty. Dr. Pretty, please.
It's cos n theta
Is cos n theta
plus I
plus I
sin n theta.
n theta. Thank you, Dr. Pretty. And I want to tell everyone that this very important statement that is coming from you, this very important statement that is coming from you, is a great result that we are going to meet from now on, and we shall enjoy using it. And that is what is called the de Moivre. Sorry. That is what is called the de Moivre theorem. De Moivre theorem from a Frenchman. For those who know how to pronounce for us French in French, the name that de Moivre theorem. That name there is Moivre. I don't know whether V is pronounced, but I know OI is moi. The de Moivre theorem in French. This is a French mathematician who first saw this coming, who first wrote about this And that is why it was named against his name, the De Moivre's theorem. So we can use that to answer very many questions, that De Moivre's theorem. You can use it to answer very many questions. I've seen questions in UNEP. I don't have a QB here with me, but I can send you there. Please get your QB and check. I've seen questions in UNEP where people are given multiply out, and then what are you going to multiply out? Then they give you cosine 5, for example, theta, I 5 theta, sine 5 theta, 5 theta, I sine 5 theta. Then you find someone given this and is told to multiply this with another, which is cosine. For example, let me just give an example, 2 theta plus I sine 2 theta. I've seen a lot of this. 2 theta. In UNEP, simplify this, and they give it to 2 marks, 3 marks, and you wonder why it doesn't have very many marks. Just because it is testing your mastery of simple theorems. Because what would I expect? I expect you to think about, to take this backwards to cos theta plus I sine theta to power 5 multiplied by cos theta plus I sine theta power 2. Then from there, you will come up with the cos theta plus I sine theta. Since it is the same thing, these are added. The powers are added. And finally, you can say cos theta plus I sine theta. No. Finally, you can say cos 7 theta plus I sine 7 theta. Coming from that, simplify. So if they told you to simplify, you can easily simplify that kind of thing. The common one that I have seen, this one is it is not true that I've seen this, but it is just testing that mastery. The common one I've seen is like when someone gives you cos 5 theta, for example, or 3 theta. Let me use 3 theta this time. Plus I sine theta, sine 3 theta, multiplied by or divided by, when there is division or not, but sometimes it is multiplied by cos theta minus I sine theta. When this is a negative somewhere there, if that is a negative, why has it been made negative, and what significance is it? So we expect that you will come back at your De Moivre theorem and say this becomes cos theta plus I sine theta raised to power 3. And this other one is cos theta plus I sine theta, the same thing, but raised to power -1. Why is it like so? Because the cosine of negative theta is also the same as the cosine of theta. but the sine of negative theta is the negative sine of theta. So that's why you find that it is affecting this part where with of sine, but it has not affected this part of cosine, because cosine of negative theta and the cosine of theta are the same. But for this side of negative theta and the sine of theta, and for this side of sine, it is affecting. So after writing that, then you go to your trigonometry and you have cos theta, and you have cosine of theta plus I sine theta raised to power 3 minus 1, which gives you cosine of theta plus I sine theta raised to power 2, which gives you cos 2 theta plus I sine 2 theta. So you can simplify this kind of work quite easily. It is the same thing as if you are given cos theta, cos whatever theta, cos pi by, let me use pi by 3, plus I sine pi by 3. And then down here, there is cos of pi by 2, plus I sine of pi by 2. Simplify. I would expect that the moment you notice that common thing like the pi, etc., should be able to use your demo over very fast. Okot Jesse, what do you want to say?
Yes, sir. Sir, you see,
Yes.
there we are supposed to, we are not dividing, but we are multiplying. But I'm saying again, you're saying 3 minus 1.
Because I'm multiplying by a negative. I am adding, but I'm adding a negative. Did you notice that?
Master.
Are you noticing that I am adding a negative power?
Yeah, we are, because when we are multiplying.
This, when I'm multiplying, I add indices. And the indices I'm adding, one is positive, the other is negative. So when you add them, you get.
When you add the negative, yeah.
Yes, am I making sense? I am adding the indices because of multiplication. But the indices I'm adding, one is positive, the other is negative. So when you add positive to the negative, what happens? It's like subtracting.
Yeah.
I am very happy with that notice, what you have taken note of, but I want you to take a note of the fact that I'm actually adding those indices, only that I'm adding a positive and a negative index. Is that fine?
Yeah.
And you will see that it is the same thing that happens here where I am dividing. If you could notice this where we are dividing, and you take a note that I can write this as cos pi, for example, plus I sine pi. And the n is now a third. And down here, I have cosine pi plus I sine pi, and it is a half. Now, when it is the same thing that I am dividing, I can subtract indices. The way Okot told us. So you have cos pi plus I sine pi. Because of division, subtract the indices. Take a third and subtract a half. Now a third minus a half is the normal subtraction. So you get 2 minus 3 over 6. And when you subtract 2 minus 3 over 6, it gives you cos pi plus I sine pi. And a third minus will give you negative 1 over 6. I want to think so. Which you can bring back to our worker as cosine of negative 1 over 6 pi plus I sine of, in the same spirit, negative 1 over 6 pi. This negative 1 over 6 pi lies between negative pi and pi. So I think it's very okay for you to write it in that form. It's already a very simplified form. Go to the UNEB QB. You'll find questions of that nature that require simplifying, where you can put things on the same, under the same base with different indices, use the rules of indices, but also use the normal. You will be able to get there. Okay, unless there's something that you want to say, I want us to wind up. Can I hear from you as we close?
Sir, so it means when we are solving or simplifying, when we have pi, for the pi, it works as the theta.
Yeah, the pi is an angle, so you can leave it to be the theta, and then you can pick the coefficient of pi. So if it is 2 pi, you can leave the pi and pick the 2. If it is a half pi, you can leave the pi and pick the half, and you go ahead and have it the way it is. So you can use your de Moivre, and you can also use your rules of indices, and you'll be there. Okay, I want you to go to our book. I don't know. Those of you who have it, and look through those examples there. When we meet again next time, we shall compound. I believe I'll also get the QB, and then we have we go through a number of those questions, and we shall call it. At least we shall be comfortable with the complex numbers. The book is which book? Sadler, Understanding Pure Mathematics by Sadler. I don't know, Sadler and Stoning. Do you know the book, Understanding Pure Mathematics by Sadler? And share its page here so that you see what it looks like on top. Understanding Pure Math by Sadler. That is the book. This is its page. You know that book. You use that book, Understanding Pure Math by Sadler. It's the one that I'm using. The other books also have the same things. And the more simple books, which you can Sadler and Thorning. There are other books that you can use. Okay, I want to wish you a good evening. I want to thank you for the attendance. A number of you have moved off, but for all of you, please thank you very much for attending. It is very important. My teacher, that even me now at my old age, I can remember my teacher's words. My teacher would tell me, strike the iron while still hot. Go to these exercises and try out these exercises. Otherwise, when you stop at attending and you don't try out, you will want to try out when it is no longer making a lot of sense. Please go and try out and you enjoy your mathematics. I want to tell you that I'm very sure. I want to wish you the very best. Please, we meet next time. Bye-bye. The pages are around the 460, 461 up to, and you continue, 460 actually. Complex numbers start at 460 and you continue. 460 is where we have the heading. Let me see, this one is which page? 460 is where we have that page, the starting page, and you continue from there. 460. This is 430. I'm sure if you went to 460 there, this is still array. 400 and the watts. 450. If you go to 460, $459 and 460. So that is where complex numbers are. And you continue from 460 to all those other pages. You will see the work that we are sharing here is all there. There are very many examples which you can go through, and then you can try out the exercises. There's an exercise that we had last time, 18D, and there are other exercises, the 18E, and so on. Okay, have a good evening.
Bye, guys.
Bye.
Have a nice time.
Bye. Nice time.
Likewise. Bye-bye.
It's a nice time.
Okay, have a good evening, nice time.
Yeah.
Good night.
You too. Yes.